Assalamu alaikum. My name is Sultan Khan, and today in this video we'll talk about the two types of electrical currents, their waveforms, how they are presented on paper, and their different values. So the topics that will be discussed today are a brief review of the differences between alternating AC and direct current DC currents, and how each of them, the DC and the alternating currents, are presented, and different values of AC, and we'll see whether Ohm's law is also applicable in AC. We have already seen that Ohm's law is valid in DC. So we'll review whether the same law is also applicable in AC. And lastly, we'll talk about frequency. So first, do a review of DC, direct current, how it flows. This will help us in understanding the difference between DC flow of DC and flow of AC. So this is a very, very basic circuit of a direct current circuit. A battery, a switch, and a load, in this case a bulb. So the current flows in one direction only, either clockwise, here anti-clockwise, or clockwise, depending on the terminals of the supply, a cell, a battery in this case. Here, just to revise, that the direction of current flow is shown from negative to positive, which is the correct direction, but traditionally we have been talking about that the current flows from positive to negative. So both are correct in a sense that when we say current flows from positive to negative, we'll say it's the traditional value, but the actual value is always from negative to positive because it is flow of current, flow of electrons. And this flow of electrons or current is always in one direction, as I said earlier, unless we switch the terminals of the supply. Like if we change the direction of the cell here, then the current will flow in the reverse direction. Also, if this cell is like 1.5 volts, the voltage in the circuit, or the voltage applied to the bulb, will always be 1.5 volts unless the battery source starts weakening. Otherwise, DC voltage stays constant, and direct current also flows in one direction unless we change either of them. So a scientist Ohm developed a law called Ohm's law in his name, that if a circuit has a voltage of V, Vs here means supply voltage or source voltage with a positive and negative sign, and there is a load RL, L is for load, resistance R, and there is a current flowing I. So the amount of current flowing is given by a simple formula, voltage upon resistance. So this is our Ohm's law. If we don't change the value of supply voltage or the value of the load, the resistance, this amount of current will always stay constant, and it will always flow in this clockwise direction, assuming a conventional current. So in this case, let's give a value. Assume the voltage here is 120 volts. Let me show you that. So here the supply voltage is 120 volts, and the resistance of the bulb is, say, 60 ohms. Then according to this law, I is equal to V upon R. Current is 120 upon 60 is equal to 2 amperes. So this current will remain 2 amperes unless we change the resistance or the value of the supply voltage. So as I said earlier, the current will always flow from positive to negative, and its value will always be constant at 2 amperes, assuming a conventional current. And the flow of DC, if we plot the flow of current against time, look at the top diagram here. So this is time in minutes and seconds in hours, and the vertical is the amount of voltage and current depending on the values. So if we do a time against voltage or time against current plotting, it will always be a straight line, meaning the amount of current will always be the same and the amount of the voltage, let me do this. So the amount of current or voltage will always be constant, which is shown by a straight line of voltage, a plot of voltage, a straight line, and a plot of current, a straight line, meaning at any given time the values of current will always be constant and the value of voltage will always be constant. So revising here, I think I have discussed everything, so let's go to the next slide. So let's discuss the flow of alternating current. We just discussed flow of DC, direct current, and we saw that it flows in one direction only, from one terminal of the supply to another terminal of the supply, single direction. And DC is normally created by chemical action in batteries and cells. So let's see how AC is produced and how it flows. Now AC is generated by alternators or AC generators, and they work on the principle of electromagnetic induction. And this principle of electromagnetic induction was first discovered or designed or written by a scientist called Faraday, and therefore it is called Faraday's law of electromagnetic induction. This electromagnetic induction simply means that electricity is produced through magnetic induction. Electricity is produced through magnetic induction, and we'll talk about that. And the law says when a conductor cuts magnetic lines of force, a voltage is induced in the conductor. There is a reason why I have capitalized the word cut, because this is the foundation. If there is no cutting of magnetic lines of force by the conductor, there will be no voltage. And what is cut? It is simply like that. Say these are lines of magnetic force from north to south. So if I take a conductor or a knife and I move it like this, horizontal or parallel to the lines of force, there is no cutting there. But if I move the knife or the wire perpendicular or at an angle to the lines of force, which are these, then you will see there is cutting. So that is exactly the concept here. When a conductor cuts magnetic lines of force, a voltage is induced in the conductor. This is a very elementary diagram of an AC generator or an alternator. It has two fields to create the magnetic field. These dotted lines and the arrows, these are the magnetic lines of force from north to south, and they are within the area covered by this. And then we have a copper wire. We made it in a shape of a coil here. So this is a single turn coil. It is started from here, bent this shape, and then finally it ends here. This is a single turn coil, but if we keep looping or turning the wire into multiple loops here, this will become a multi-layer coil, multi-turn coil. But there will be two ends only. So what we have done here, soldered one end of the copper wire to a copper ring which is called a split ring or slip ring. It is soldered there, and the other end of the wire is soldered to the other slip ring or split ring. Then two brushes, carbon brushes, are fixed here, so they just touch the slip rings, they don't move. And from these two carbon brushes, terminals are provided to connect your bulb or load or heater to use that electricity if it is produced in this coil. The electricity will be produced in this coil, not in the wire coming out. So this is the elementary diagram of a physical generator, and this arrow shows the direction of rotation. In this case it is clockwise. Same generator, alternator, slightly presented in a different manner. Same magnets, same coil, but now you will see it is a multi-turn coil. You will see it is being looped many times, 10, 100, and so on. But in the end, there are two terminals coming out, two copper terminals connected to the two split rings or slip rings, two brushes, and then brushes terminals are taken out and connected to a voltmeter. In this case, voltmeter will be our load. The piece that will be moving is only these two brushes, these two split rings, slip rings, and this copper coil. The poles, the brushes, and this external voltmeter circuit, they don't move. Now, this diagram seems very complex and complicated for the beginners, and it is. It's complex to understand, and we will talk about that. So you must have seen or done an experiment called pendulum motion. Pendulum is a copper or brass ball connected with a wire or thread fixed here, and then you bring this brass ball here and then leave it. So it will move a to and fro motion, and if there is no air friction, it will keep doing this. So this was the center, 0. It went to the left to a height, a maximum height, stopped there, came back by gravity, didn't stop here because of the inertia. It kept going towards my left, same height, stopped there for a microsecond, and then because of the gravity came back. And if there is no friction, it will keep moving in this manner forever. But in real life, because there is air and gravity, it slowly stops. In maybe a minute or two, it will stop here. If you have plotted this movement of a pendulum, you must have created a perfect wave like this. And it is called sine wave because it is governed by the sine of the angle. So coming back, so this 0 here is actually when the bob, pendulum's bob, is here. And when this point is where the pendulum is at the top on my left direction. Then it stops here, and then it starts coming back. So that this point is where it has came back. Now it goes to my right side at a height, and that is this point. So that height stops there for a moment, and then comes back and goes to this point, which is this point again, the 0, and so on. So one complete movement of the pendulum was shown by one complete sine wave. So this is the height of the pendulum. This is the time in seconds. This machine creates current in this coil exactly in this manner, meaning when the cutting is 0, the current is 0. When it starts moving towards the center of the magnet, one magnet, the induction increases, reaches a maximum, and then when the coil starts coming out from the center and comes to this location, the voltage induced decrease to 0, and now the coil is moving towards the other magnet, which is the north pole. The direction of the current will change, which is this point. It will increase till the coil reaches the center of the north pole, which is this point. And when the coil further moves and becomes vertical, so at this point the current or voltage becomes 0. And then the same side of the coil has completed one turn, and then it keeps doing this so many times per second. And if you do a plotting, you keep creating sine waves so many times per second. Now this movement doesn't mean the current is moving like this. No, that's a very bad concept. So this is a wire. The current in this wire is not moving like this. No, it is moving like this. Moves in one direction, increases, decreases, changes the direction, increases, decreases, change the direction, increases and decreases, change the direction. So it's actually flowing in both directions in the wire, and while doing that, it is also increasing its value. 0 ampere, 1 ampere, 2 ampere, 3 ampere, 5 ampere, then 5, 4, 3, 2, 0 ampere, changing the direction. Again 0, 1, 2, 3, 4, 5 ampere, changing the direction, and then again 5, 4, 3, 2, 0, and again changing. So it's doing like this. Reverse, reverse. So reversal is always where the current is 0, which is this point, this point, this point. So remember, remove this misconception that if this is a wire, the electrical AC is flowing in this wire like this. No, it's not. It's not. It's moving this direction and then this direction, and so on. If the frequency is 50 cycles per second, this change is happening 50 times per second, so fast. And also during each movement, it is also increasing and decreasing, increasing and decreasing. A very complex concept. Okay. And another point, the voltage in this coil will only be induced when there is a relative motion between the copper wire and the poles. No motion, no voltage. So to complete this was the plot that we did for DC. So time and the voltage or the current. And so this, the red line was plotted for DC, meaning how many hours have passed, the DC in a wire will always flow in one direction with a constant magnitude. So if it is 2 amperes, it will always be 2 ampere, unless the battery gets discharged and the voltage start decreasing from 1.5 volt to 1.4, 1.3. If the supply is fixed, the current will be fixed of a fixed amperage, and the direction will always be either from left to right or from right to left. It will not change. AC, in contrast, is different, as we have seen. Time, the voltage and the current. Here AC flows in one direction, from 0 to maximum, then maximum to 0, and then switches or reverses its direction, and then again goes to the maximum, then again to 0, and then again switches back. So remember, wire, this is the wire. AC does not flow like this in the wire. It flows in one direction, then reverses, 0, reverses, 0, reverses, 0. So this is exactly that. So that's why I have put both DC diagram and the AC wave diagram together to give you the concept of the differences. Okay, so let's continue talking about how AC is produced. So in this diagram, we will discuss in details the AC cycle, the sine wave here. So this is the cross-sectional view of the same generator, alternator. The two magnets, north, south. There is only one coil here. But why you are seeing so many coils here? Because we are plotting one complete motion, one circular motion of that coil. So how it works, that say, so A and E is the coil. A is one end, B is the other end, and because we are cutting the coil like this, you only see the copper wire circle here and the copper circle here. So it's a coil. It is horizontal at this time, A and E. And then we start rotating the coil in, say, anti-clockwise, counterclockwise direction, counterclockwise. So this is the moment of 0, 0 here. Look at this 0. And if we are plotting this 360 degrees here on the paper, so from 0 angle, 0 degree to 360 degrees, this will be the complete one cycle, one circle. So A is actually here with 0 degree. Now we move it, the coil, and it moves to 45 degrees, which is B and F. Starting it was A and E, one coil. The same coil is now at position B and F. So at B, it has moved 45 degrees, and there is a voltage induced, but not the maximum. And that value is the point B here. Now the same coil is now this, which is, it moved another 45 degrees. So it has moved now 90 degrees, which is another 45 degrees, 90 degrees. At this point C, it is cutting the lines of force vertically, perpendicularly. So this is the maximum cutting of lines of force, and therefore there will be a maximum voltage here, which is, say, 100 volts. So C, at this point C, the voltage induced is 100 volt. That is the maximum. Now our coil is C and G. Now because it is still moving, it will now move away from the center. It will come at D and H. D means another 45 degrees, which is 135 degree. Now this voltage will be the same as the voltage produced in B. So that's why B and D are at the same level. Then it further moves down another 45 degrees, and the coil is now horizontal, E and A. So E here, E, another 45 degrees, which is 180 degrees. So now the coil has moved half circle, 180 degrees, and the voltage is now 0, because here the coil is not cutting lines of force, it is moving parallel to the lines of force. Remember, the lines of force are from top to bottom, north to south, vertical, whereas the motion of the coil is across it, as like this. So lines of force are vertical lines, whereas the coil is moving horizontally. That's why it is cutting. So whenever there is a cut, voltage is induced. But when the coil comes to this 180 point here, it is moving parallel to the lines of force, and there will be no voltage, which is shown by 0 here. Now this E moves further 45 degrees, and now it comes under the influence of south pole. So it will produce voltage and current, but now the polarity, the direction of the current will change, and therefore at another 45 degrees, which is now 225 degree angle, which is this one, F, it will produce the same amount of voltage which was produced here, but now the direction of the current is different. It has become like this now. And then another 45 degrees, G, position G, it cuts maximum, so there is a maximum voltage at G, which is equal to the same as at C, which is 100 volt. So now 100 volts are created, but in the opposite direction. And then it comes down another 45 degrees to H, which is this, and then finally comes back to A, which is the starting point. And now this coil has moved one complete 360 degree circle. This one cycle has produced one complete cycle. So one circle of the coil produces one cycle of AC, 360 degrees. Now again, to emphasize, in the wire the current is not flowing like this. It is flowing like this, half cycle, flows in the opposite direction the next half cycle, and so on, to and fro motion. And also during this flow it is increasing to 100 volt, again reducing to 0, reversing, increasing to 100 volt, 0 volt, reversing. Very important. So as I described earlier, the pendulum motion and how AC waveform are basically the same. Let's talk about this. So this was the pendulum. This was the top of the structure, and this is the ball, the brass or the copper ball. You moved it manually, and then you just left it, and on a paper you're plotting the motion of the pendulum and its height. This is the time, and this is the height. Height means how high it is. Comes back. This is the 0 level, gets high to another maximum, it stops here, comes back because of the inertia, continues to move, high, back, reverse, high, back, original high, back. And if we plot this height or the angle, you get a sine wave here. Okay. This is a brilliant graphics which actually shows the flow of alternating current AC. This is water. Whoever has produced this diagram or this picture is a genius. So this is a piston, and this is a mechanical machine which is moving this piston to and fro. And this tube, hollow tube, is full of water, and this is a construction, is like a pinch, so it becomes like a resistor. So the pump, the piston here, has to force to flow water either from bottom to top or from top to bottom. And look at the water here, and just keep looking at this. So for some time the water flows in this direction, and then it flows in this direction. This. And where is the sine wave? The sine wave is, so when the piston is here, it exerts the maximum pressure. And when the piston is here, it exerts the minimum pressure, and then this piston pushes water in this direction. When it is here, it pushes water here. When it is here, it pushes water in this direction. So take some time, understand what it's saying. The message is the water here in this resistor is flowing in both directions, this way, this way, this way, and this way, and the pressure of the water is also increasing, decreasing, increasing, decreasing. So AC flows in both directions and has to and fro. Wire current AC flows in this direction, then the reverse direction. So it flows in both directions, to and fro motion, whereas DC flows only in one direction. So we are coming to the close of the video, so we'll talk about the values of AC. We have seen this diagram of sine wave of alternating current already, with a positive voltage of 100 volts and a negative voltage of 100 volts. And this is half cycle, and this is the remaining half cycle. So from A to A, it is 360 degrees, and this is one cycle of AC. Now, because the 100 volts only happens at two certain moments in that cycle. At the moment when the coil is at 90 degrees, so at C it is 100 volt. At G it is 100 volts. Rest of the time it is not 100 volts. It is less than 100 volts. It will be zero at point A, at point E, and again at point 360 degrees. In between any moment, it is more than 0 and less than 90. So between this time, it is between 0 and 100. Between this time, it is between 100 and 0, and so on. So the 100 only occurs 2 times in one cycle. So if the frequency is 50 cycles per second, the maximum 220 volts will only be happening at 2 moments in time only. 220 volt at C and 220 volt at G. The rest of the time in that cycle, it is less than 220 volt, and it is also 0 at two points, here and here. And this 0 is counted for the next cycle. So meaning we cannot say that AC is 100 volts. No, it is not. It is 100 volts or 220 volts at only 2 points. Meaning we have to describe the values in a manner so that we tell what time it is. So the first value that was designed by the scientists is called instantaneous value. Instantaneous means at that moment. And it is shown by V for voltage, I for instantaneous. So VI is equal to peak value. Now what is the peak value here? The value at C or the value at G, which is in our case 100 volts. V peak times sine of the angle, because this is the pendulum motion. So all these values are governed by the sine of angle, sine of 45, sine of 90, sine of 135, sine of 180, sine of minus 225, minus 270, so on. When you use those sine values, you will get here, if this is 0, it will be not 100 but not 0. It will be 70, we'll talk about that. It will be actually around 70 volts. Then it increases from 70 to 100, decreases from 100 to 70 here, decreases to 0, reverses 70 volts here, and increases to 100, and again so on. So if you put the angle here, and this is instantaneous value, I put 100 here, times sine of 45, sine of 90, sine of 135, you will get the actual values at B, C, D, E, and so on. The other value is called the peak value. We already talked about that, V peak, which is 100 volt here and minus 100 volt here. So 100 volt is at point C, and minus 100 volt is at point G. So they are equal but in opposite direction. And then we have the effective value, because you will have a question, okay, what is the value here? Because it is varying between 0, 100, 0, 100. So what is the effective value? That effective value has been calculated, that it is equal to peak value times sine of 45 degrees, which is this. And that is calculated as 100 times 0.707, which is the value of sine 45, and the result is 70.7 volt, meaning though this AC has a maximum of 100 volts, it is not really 100 volts, because it is not 100 volts all the time. So if we have DC of 100 volts and we pass it through a heater which produces heat, it will be producing heat which is always because of 100 volts. If we pass this AC of peak value of 100 in the same heater, the heat produced will not be the same, because the AC is not 100 volts at all time. The current is not always 2 ampere all the time. The 2 amperes is 0 ampere, 1, 2, then it decreases to 2, 1, 0, changes the direction. So the heat is proportional to the amount of current. And AC current is not fixed at 2 ampere in this case, because the voltage is not fixed at 100 volts in this case. It is fluctuating. The heat will be less. So the engineers or the designers, they calculated the value that it is always the effective value, which is equal to the DC value, is equal to the peak value times 0.707, which is sine 45, 70 volt. So we can say that AC peak gives like 70% what DC gives. So that, remember, this peak effective value is also called root mean square, RMS value, and in another video we will talk about that. And this RMS value, which is 70.7 volt, is equal to the DC value, which is 70.7 volt. Okay. So now we have just discussed that AC has different values, peak value, instantaneous value, and the effective or RMS value. DC has no such thing. It is always one value. It is 12 volt, it will be 12 volt. It is giving 2 amperes, it will be giving 2 amperes unless we change the voltage. So DC has no effective peak RMS values. AC has. Now how do we compare then Ohm's law, or use Ohm's law on AC? So let's talk about that. So Ohm's law actually applies to AC, but with a condition. So Ohm's law is I, current, equals voltage upon resistance. It applies here, but with effective values only, or the RMS value of voltage and the RMS value of current. Let's talk about that. RMS value of voltage and RMS value of current. And now in AC, Again, this is something that we can talk in another video. AC circuits have not only resistance, they have two other resistances in addition to the physical resistance of the copper wire or of the aluminum wire. They have two other restrictions that oppose the flow of current or the voltage, and those two oppositions are also added to the resistance using the vector method. This is something that we can talk in another video. So in AC circuits, the resistance is there, but there are two other types of resistances or reactances that affects the flow of current in AC circuits. One is, which is not present in the DC circuit, the concept of an inductance, magnetic inductance. So when you move a magnet, physically move the magnet in a to and fro motion, left to right, right to left, a voltage is induced in the coil. This is what AC generator is. This is exactly what an AC generator is doing. So if you are moving the magnet within the coil like this, you will see a voltage is induced, and it is like this. This inductance, the magnetic force creating when you move the magnet, produces current, but at the same time it creates an opposition to the flow of the movement of the magnets. So this in a manner opposes the generation of current within itself. This opposition is in addition to the opposition by the material of the coil, which is copper in this case. So the copper itself, the atoms in copper, they oppose the flow of current. That is resistance. Now the magnetic field produced by this copper coil puts another resistance to the flow of, or the production of current, and that is called inductance, and we'll talk about that. And the third element which opposes the production of current in AC circuit are the capacitors. So if we are using capacitors in circuits, which we do, so those capacitors, because of their capacitance, also oppose the flow of current through them. So these two additional oppositions, the capacitance of the capacitors and the inductance of the inductors, the coils, are added in AC circuits to the resistance of the copper wire, and then the sum of those three values, and that sum is not mathematical sum, it is a vectorial sum. We can talk about this in another video. And the total resistance is not called resistance, it is called impedance. Impedance here shown by the symbol Z, and this inductance, the resistance produced by the coil inductance, is shown as XL, and it is called inductive reactance, and the resistance or opposition produced by the capacitors is shown by symbol XC, capacitive reactance. So XL is inductive reactance produced by the inductance of the coil, XL. X is R actually, X is R, but we are not using R because R is only because of the copper wire. So X is the R because of the inductance of the coil. XC is the R because of the capacitance of the capacitors. And the impedance, or the total resistance, is not simply equal to R plus X plus XC. No, it is equal to R square plus the difference of XL and XC, then square. Now this minus sign shows that the reactance produced by the inductance, the coil, is in opposite direction to the reactance produced by the capacitors. So they are in the opposite direction. They don't add, they subtract. And so in AC circuits, I is equal to V upon Z or Z. It's not equal to V upon R. That's the key difference. Okay, so Z or Z is impedance, R is resistance, XL is the inductive reactance, which is the reactance or resistance produced by this coil, and XC is the capacitive reactance, the opposition produced by the capacitances. And again, to refresh your memory, that DC is single directional and of constant magnitude. AC is bidirectional and of varying magnitude and also changing the direction. So AC, naturally we have already talked about that there is a frequency, because what frequency is? It is basically, this is one cycle, which is one complete circle of the wire. So if this coil is being rotated at like 50 times per second, it is producing 50 of these cycles per second. The frequency is 50 Hertz or 50 cycles per second. So one cycle per second is called 1 Hertz. Hertz is the name of a scientist. Okay. So frequency is represented by F, is the number of times AC completes its cycles in 1 second. These cycles in 1 second. In the British areas and in Pakistan and India, it is 50 cycles per second, 50 Hertz. And in America, it is 60 cycles per second, 60 Hertz, 50 Hertz. So one cycle is created for one rotation of the coil between one set of north and south pole. And frequency F is calculated by this formula. N is the speed in RPM, revolutions per minute. P is the number of poles divided by 60. 60 is actually simply to convert this RPM into RPS, revolution per second. So N is an RPM per minute. So there are 60 seconds in 1 minute. So divided by 60, the value becomes per second. N in this case are 2. These are 2 poles. So this N will be N is the RPM, the speed. P are the poles. In this case, there are 2. If there were 4 poles, there might be another north and south here. So this pole will become 4 or 8. So speed times number of poles divided by 60 will give you so many hertz or so many cycles per second. So we already talked about that. Speed in RPM, P is the number of poles, in this case 2, 60 is the multiplier to convert into seconds. F is the frequency in cycles per second or hertz. So I already described that in Pakistan and India it is 50 hertz, and in US influenced countries it is 60 hertz. And one point to note, so these two frequencies are for the domestic electricity or in the industrial electricity. When we start talking about electronics, they are not in hertz, they are in kilohertz, in megahertz, in gigahertz. So like for smaller frequency systems like simple radios, it can be kilohertz. In higher frequency electronic devices, it can be megahertz. Mega means 100,000, 1 million. and in advance in other higher frequency systems like internet, it can be megahertz and gigahertz. So concept is the same. If it is 1 kilohertz, meaning the wave there is changing this 1000 times per second. That is 1 kilohertz. If the wave, electronic wave in some other system is 1 megahertz, it is doing this 100,000 times per second. So you can imagine how quickly the current or the voltage changes its direction in 1 second. There are thousands of very good videos which show you the concept of AC and DC being discussed. These are the two. And this brings me to the end of this presentation. The information here, and thank you. Allah Hafiz. Bye-bye.